Yeah, so thanks, Andreas. Thanks to the organizers for the opportunity. I'm going to talk about actually a very old paper with Alex Engstrom, maybe some of you know. Wrote this a long time ago, maybe before I met most of y'all. I don't think before any of y'all were born, but it is quite old. And then some recent discussions with Bennet, who's here, and Marta, Pavelka, so putting your names up here to make sure we continue the discussions. I should also apologize. I don't really have much computational stuff. We're kind of computational adjacent. I don't consider myself really a programmer, but hopefully we'll see that there's some connections there that means I can still hang out. So just some background, just because I don't think we had to talk about resolutions. I know there's experts in the room, but just to kind of set notation. So fix a field K, which I usually don't care too much about characteristic or anything like that. We'll see sometimes that matters. Take the polynomial ring on n variables and look at homogeneous ideals in that polynomial ring. And a resolution, right, is this long exact sequence where each term in this long exact sequence is a free module. Since I'm working in the graded setting, I want to consider this twist on the copy of that free module. And I want to record, at each homological degree how much it's twisted. So this is recording this information. This is what's called a resolution. It's going to be minimal if those numbers, those beta ij's, are minimum among all resolutions. And in that case, actually, this number can be computed as this derived object. And we call those the graded Betti numbers. And then this usual thing when you're resolving the ideal versus the quotient ring, you can sort of, one gives you the other. And then this is why I can, plus minus 1 is often kind of confusing here. But anyway, so that's the object we're considering here. And again, if you haven't seen this before, so you want to think of a resolution as, similar to maybe a presentation of a group or something. So if you haven't seen this before, we're trying to build this long exact sequence. So you've given me this ideal, and how do I construct this resolution? So, for simplicity, let's say that's generated by polynomials of degree d. And what I do is I just take my first module to be just that many, I have j generators, take j copies of this free object, and just take a map, right? So I can now define a map from this F0 just, with this basis, just surjecting onto those generators. I have one dimension for every generator. And then that guy has that map, that morphism has a kernel, and that'll be the first syzygy module, and it has some generators, say G1 through GK, and rinse and repeat. Take a map from that free object onto that F1 and then keep going. And this is how I build this resolution. So I'm looking at the relations among relations, people like to say. And then this process actually eventually we'll get an injective map. There will be no kernel. That's the syzygy theorem. And in fact, it stops at most in n steps. And that will be your resolution. That's kind of how you might think about these things. Okay. For me, I'm more coming from the combinatorial side of things. So my objects are combinatorial, so are my sort of data. I want to keep track of the Betti number. Well, so the Betti numbers are often the things of interest, although actually today we will be looking at the differentials as well. So this, Macaulay 2 has come up several times, so you've probably seen these tables. This may be somewhat at first confusing way to keep track of these Betti numbers. I'm going to make a table where the row j column I entry is beta I, comma I plus j, right? And so just with an example, I actually don't remember where I got this, this resolution from, but okay, so here's some resolution. And the idea is I've got these 8 generators of sort of degree 2, and that's corresponding in this first homological degree. 1 plus 1 is 2. That means that there are 8 generators of degree 2. In the next homological degree, I've got, looks like, if I did this right, 13, corresponding to this degree 3 twist, plus the 1, which is degree 4, and that's 2 plus 2, etc. I guess if you've seen this first time, it's going to be overwhelming, but I think folks in here have mostly seen things like this. And again, it's a table that kind of records this, at least these numbers, in an efficient way. I'm interested in, well, folks are interested in, if you can't get me all of these numbers, maybe you can just tell me how wide and how deep it is, right? So the projective dimension is, how many steps we have to go before we get zeros. The projected dimension is the max I, where I have some non-zero Betti number in that homological degree, so this would be, I guess, 4. And then regularity is the other dimension. It's how deep I have to go. It's a measure of how, if I think about these differentials in the resolution, you can think of them as matrices with polynomial entries, and the regularity is sort of the highest degree that you see in these matrices, and it's formally it's sort of what's the biggest homological degree where I get some contribution. So how deep do I have to go in this? Okay, so these are of interest. Actually, in this talk, I'm going to mostly kind of think about, in some ways, an extreme version of this. A linear resolution is when you, in those matrices, you only have linear terms. So in some sense, this resolution is the simplest you could hope for. Okay. If you came in late, we're still reviewing the background, so that should be good. Okay, and again, if you haven't seen resolutions, why would you care about this? So, I think they're kind of intrinsically interesting things. They're, like I said, sort of building your ideal or ring. And but you can also, I think the actual original motivation was connected to this Hilbert function. You can study the dimension of this dth graded component. In particular, the coefficients of the Hilbert polynomial are determined by those numbers, the Betti table. And you can also, if you're interested in like Cohen-Macaulay or depth properties, right, there's a relationship between this projective dimension, remember that was the width of the resolution, and the depth. And, and just maybe more sort of philosophically speaking, it's a measure of the complexity of the ideal, so that maybe somehow fits the theme of the workshop. Or, okay. And, okay, one more sort of advertisement slide here. So again, I'm coming more combinatorial side. So monomial ideals will be sort of my emphasis for today. And again, I know people know this, many people know this, but this Grubner degeneration, Grubner theory allows you to take an ideal and consider initial ideals, which are often monomial ideals. And just I have an example up here, if you haven't seen this kind of thing. So if I have this ideal here on the top, I have what's called a Grubner basis. And by definition, the initial terms under some term order, so I pick out initial terms from this basis, and I get these terms, and this is going to generate an ideal called the initial ideal, with respect to some choices I haven't told you about. But anyway, this is the kind of thing if you haven't seen this story before. And this is nice because, this is related to what I've been talking about because you have this bound that the Betti numbers of the initial ideal are bounding maybe the ones you care about, the Betti numbers of the ideal. And actually, I'm interested in I do also consider binomial ideals sometimes, and often when you look at these things that come up in nature, you do get equality here sometimes, and that's kind of an interesting story as well. You can also detect Cohen-Macaulayness, via this Grubner degeneration. This nice recent paper of Konka-Varbaro says that if you have a square-free initial ideal, then these extremal Betti numbers, which I won't define, but they're sort of the corners in the Betti table where those rise actually are the same. So this is actually a generalization of the regularity and projective dimension. You get kind of more information. Okay, so so now slowly getting into the things I want to talk about. So again, so I'm going to be considering monomial ideals, I should have said, defined by, let's say, pure simplicial complexes. So the data here will be a pure, say, d-1 dimensional simplicial complex on vertex set 1 through n. I really only care about the facets of this guy, so you really can just think of this as a collection of d subsets. Then there's this thing called the facet ideal, which is, for every, this is going to be a facet because I'm, I should have a 0 here, sorry, yeah, so Oh no, d minus 1, so I'm good. So yeah, so this is going to be a facet of that complex. The top dimensional faces correspond to monomials just by taking these as the subscripts, and take the ideal generated by that. I don't love facet ideal, but I think I've lost that battle. So it's really just a square-free monomial ideal generated in fixed degree. Okay, so but of course there's a simplicial complex in the background there. We don't really use the fact that it's closed under subsets. But anyway, so here's an example of d equals 1. I apologize because I think I'm going to switch notation later. But okay, so as I said, this is an older paper. In my years, I've switched to. Well, I gave you the the plus 1 minus 1 is still in effect here. Anyway, so this is a one-dimensional complex. It's a graph. N equals 5 here. And what are the edges that I see? What are the facets? They're just two subsets. So 1, 2 is there. That means x1, x2 is there. Okay, so the data is this simplicial complex. I get a monomial ideal out of that.
Can I ask you a question?
Yeah.
So you're doing, this is not the Stanley Reisner.
Okay, good. Yeah, it's not Stanley Reisner or Reisner. Yeah, it's
okay.
it's not the Stanley Reisner. Yeah, so that's why it's sort of confusing. Yeah, because of course you usually the better way to get an ideal monomial ideal out of a simplicial complex is to take the minimal non-faces. I'm just taking the facets. There's sort of a relation.
Hypergraph. They're just calling
it's a hypergraph. So in the paper we wrote, it's a hypergraph.
It's not a simplicial complex.
I feel like it could have been more popular if we called this a facet ideal. So, but yeah, it's like a hypergraph edge ideal or something. Yeah.
And wait, does the pureness condition translate into something for the, like if I were to write down the corresponding simplicial?
Yeah, it would be. Well, it's got to be
delta.
the minimal non-faces would have to be the same dimension.
Yeah. Oh, okay.
So it's a little bit harder to kind of write that down. But yeah, so it is the Stanley Reisner ideal, but it's maybe not so clear. I mean, those are the minimal non-faces. But yeah, so just the data is these D subsets, and already let's see, so yeah, so now D is 1, so it's a one-dimensional complex. It's a graph. These are called edge ideals. And this is kind of one of my, this is a theorem I've seen a while back that kind of got me into this sort of world, actually, that, we have this notion of a chordal graph. So we've seen this morning with Gail. You talked about chordal graphs. Great. So I think you define them similarly, or there's many ways to actually define chordal graphs, but if I want to stick to the terminology, it's chordal if there's no induced cycles of length more than 4. So whenever I have a, say, 5 cycle, I've got those chords breaking it up. As you may know, there's other ways to characterize chordal graphs with these elimination orders, things like this. And okay, so more notation. If you have a graph on vertex set n, just a collection of 2 subsets, then I'll take G bar to be all the ones that are not there. So the edges will be the missing edges. And then there's this theorem of Froberg that says I can detect when the edge ideal has a linear resolution, namely if that complement graph is a chordal graph. So it's a if and only if statement. And maybe I should have put a year here. I actually don't know exactly when this happened, but some years ago. And I would say that at least, maybe it's kind of cooled off now, but maybe 5-10 years ago there was some, I would say considerable efforts to try to generalize this to higher dimensions. How do I characterize linear resolutions of square-free monomial ideals in terms of some combinatorial property of the, say, simplicial complex / hypergraph? I think there's reasons why you sort of can't do it, but maybe that's a discussion for another time. I want to talk about resolutions, and in particular, what are called cellular resolutions. So the way I see this, so these are monomial ideals. They are very explicit, and in many cases we have descriptions of minimal resolutions. There's this Eliyahu-Kerver for monomial ideals. There's Egan-Northcott for determinantal ideals that explicitly tell you what the resolution is as an algebraic thing. And at least from my perspective, they're a little bit technical. They're maybe hard to work with, or at least for me, I can't see them. Somehow they're in front of me, but I have trouble maybe kind of understanding them holistically or something. I don't know. So often we can actually think of these modules as and the maps, the differential maps between them, as actually coming from the face structure of some complex, so some polyhedral complex, or maybe CW, regular CW complex, Right, if you have a CW complex, you have this chain complex that computes cellular homology. And you can, if you're lucky, you can identify a CW complex whose faces are encoding these syzygy modules, and the differential maps are coming from those maps that compute homology or cohomology. And so these are called cellular resolutions. Bayer and Sturmfeld is where I learned them. And correct me if I'm wrong, I think they kind of first came up in the scarf complexes of generic ideals. But it's a rich story. And from my perspective, kind of coming into this world, it seemed very sort of natural. Maybe for me, one of the most natural, looks like I'm losing laser here. A very natural example of this is if you take the maximal ideal, you get a resolution of this guy, sort of this Kosul type thing, by just taking a simplex, right? If you think of the simplex as labeled with variables, x1, x2, x3, well, I guess in this context you want to label the faces. So here I'm just labeling, as is typical, a label with the LCM of the vertices that it contains. And I take now the complex that's computing the homology of this thing, right? There's a single two-face, which corresponds to this guy. There's three edges corresponding to this 3 dimensions, rank 3 thing, and then you got 3 vertices. And there's differentials here, right? If you say orient this simplicial complex, you have differentials that that have field entries, and with this monomial labeling, you can actually bump that up to a resolution of the ideal. So, morally speaking, it's the sort of facial structure of the simplex that's telling you how the algebraic relations of this ideal play out.
And what's it?
Yeah.
The CW side, it is computing what homologies?
Well, the cellular homology. So you now have, again with an orientation, I guess. But you have, for every homological degree, you have the number of cells of that degree, and then these boundary maps.
But once you bump it up to variables, like is it? Then the only things that you would get resolutions for are like spheres, right? Because
well, yeah, in particular, it better be acyclic. It's got to be, not spheres, more balls or something. Yeah, so, so in particular, it should be acyclic over the field. And then also, actually, it should be graded acyclic, right? So you have to look at, many things should be acyclic, But yeah, good point that often when we work with these things, the complexes will be contractible. And then that's why the field doesn't matter. And you have, vanishing homology in all fields. And that's typically, when I work with these things, that's the case. Okay. So let's see. Again, the setup here is I got this d-1 dimensional, maybe sometimes d-dimensional simplicial complex, and I delta is my facet ideal. And again, I'm kind of repeating myself here, but this example of this, 2 subsets object. And just some notation as I proceed here. I'm going to write a facet as just a list of its vertices, but I always want to assume that it's increasing, right? So my ground set is always 1 through n. It's an ordered set, so I can always write my ground set in increasing order. And just to motivate this now, the facets of my complex are the generators, right? And so if I want a cellular resolution, I want some space that, a space of these things, right? The facets themselves, you think of the 0 cells, and I want a space that somehow, describes the syzygies of the underlying ideal. So in what follows, I want to get a space where the 0 cells are the facets. And so here's maybe the most technical slide here. So again, I've got this. So I do want D, I'm sorry about that. D-dimensional complex on vertex set 1 through n. I'm going to define this thing x delta. It's going to be a polyhedral complex. Okay, and it's just for concreteness, it sits inside this big product. And again, the vertices of this complex will be the facets, right? That's what I was saying, that this list, increasing list. And then the higher dimensional cells. Okay, so they're now going to be, so this is a sort of complicated thing. So again, I've got the vertices here, and I want to build the higher dimensional cells. They're all going to be products of the form, sigma 0 cross sigma 1, where each one is a subset of n. They are increasing. I'll explain what I mean by a subset increasing. Basically, I want everything here to be less than everything here. and then satisfying ... And I think I'm just going to do this with a picture. So,
Less
here's
than by
my...
inclusion?
Say again?
Less than by inclusion?
Less than, like, you mean here?
Yeah.
So, no, I mean, like, this is like 1 and 4, so this should be like 5 and 6. So every element in sigma I should be less than every element in sigma I plus 1.
Got it. Just
Not Lex order. It's actual, like.
Like every element in that thing should be less than every element in the other one. And I'll do an example here, maybe on the board actually. So here's the data, right? This is the simplicial complex, and here's the polyhedral complex I get out of it. So for instance, like there's triangles and squares here, right? So let's say like there's this triangle here, right? So it's the way I would write this is it's 1, 2, 3 cross the singleton 5, right? So notice that every element here is less than every element here. And this makes a triangle. So you think of this as the triangle cross a vertex. There's also 2 cells here. So there's this guy, what is this? This looks like 1, 2 cross, is it 4, 5? Again, everything here is less than everything here. That's what I mean by that. And that makes a square, or rectangle. And there's actually also a tetrahedron, right? There's that's 1 cross 2, 3, 4, 5, I guess, right? Okay, and so does that make sense? That's the data of these cells, and then the condition that I dotted here means that every choice from these, these are 2 these are collections. There's 1 for each. So this should have been. Oh, this is actually okay, right? So this is 1-dimensional, so I have 2 things here, right? Since the underlying simplicial complex has 2 things in a facet, there are always 2 sets here. In general, you'd have D plus 1, right? And so the condition that I'm trying to not tell you, but I will tell you in words here, is that every time you take a singleton from each one, it should be a facet. So if I take 2 and 5, that's an edge in that graph, right? The 2, 5. If I took 1 and 4, hopefully that's an edge here. If I took 1 and 5, that's an edge here, right? Okay, and that's the condition.
It's astonishing you got away with such a severe order. Can you say why?
You mean, well, I mean, I'm just finding a complex. Right now, I haven't said any. I mean, this is just a construction, right?
But it works. That's amazing.
Okay, that's hopefully something works. Yeah, I mean, that's where we're going here. Yeah, I mean, so good. So this construction makes sense for any, say, pure simplicial complex, but when does it work? Okay, so here's when it works. More notation. Maybe you guys have seen the notion of an interval graph. So a graph is interval if you can represent its vertices as intervals in the real line, and you say that those are going to be the vertices of the graph, and then you're adjacent if those intervals intersect. So here's a picture I stole from the internet, and nice big picture, right? So I mean, I was going to say I wouldn't want to try to draw this, but I also don't want to try to check this, right? But so 1 is intersect. These are real. They're intervals in the real line that kind of got separated, right? But 1 and 2 are intersecting if you flatten them down, and that's an edge here. And 4, 5, etc. And interval graphs are particular cases of chordal graphs. It's a subclass of chordal. And here's something I kind of only learned actually kind of recently, that there's another way to characterize interval graphs. If you label the left endpoint of each interval moving left to right, like they did here. Does that make sense? So I labeled the intervals moving left to right as I see the left endpoint. Then you can actually characterize G being interval if and only if you have this condition that whenever you have an edge AB, now remember A is always less than B in my convention, then AC should be an edge for all. Well, I could have just said C less than B, but I also, C should be bigger than A because I wrote it that way. Okay, so you can always knock down the second entry. That's the characterization of being chordal, or being interval. Okay, so that's going to motivate a definition. So maybe just pause there.
Is that the same condition as that in different Jews?
Well, again, I haven't told you. This is just the data of the labeled simplicial complex. Right? So far, I've just have a simplicial complex with vertices labeled 1 through n. I built this complex, but now, well, you can see where I'm going. Hopefully, so I want to now define. Okay, so is this kind of condition okay? We're going to bump this up into more than one coordinate now. So the definition we want is now we have a pure simplicial complex on this vertex set, And I'm going to say it's interval if, okay, so a relabeling of its vertex set, and this is typical that, this is with respect to a labeling, you have the abstract complex, so I want to label it, and you want to find a labeling so that, similar thing, that if you have a facet like this, that's in the complex, then every time I bump down all but the first guy, or that's what this is saying, it's also in there, it's also a facet. So I can knock down, anything where, I still maintain my increasing set here, and that should be a facet. And I hopefully have an example here. So this is a three-dimensional interval complex, like I have 2, 3, 5, 6, so I can lower 5 and get 2, 3, 4, 6. I have 1, 2, 3, 5, I can lower 5 and get 1, 2, 3, 4. Okay, so it's very similar to shifted. I mean, shifted just is, doesn't have this funny A naught playing a weird role there. If you kind of, if you treat A naught as the others, then you get what's called a shifted complex, if you've seen that before. But this is a broader class. This strictly includes shifted complexes. I learned this definition from this recent paper, Benedetti, Seccia, and Varbaro. They looked at determinantal facet ideals, and they noticed, or they proved that if you have complexes, so there's this notion of determinantal facet ideal coming, again, from a simplicial complex, tells you which determinants you should take. And if you have one of these complexes, these interval things, then you get square-free initial ideals. I think Aya also works on similar things. And so I don't know who to attribute this to, but I learned this word from. OK. But you guys, you have the unit interval, which is like a stronger thing. OK. Okay, so
Keep saying recent, relative to what?
This one is actually
data.
last year.
Okay.
And we'll see how old, it's maybe embarrassing how old my result is. Yeah, so 2012 is when this got published, so so here's the result, which maybe you can anticipate, that if you have a d-dimensional interval complex, well, I got to take its complement, okay? So again, the complement just means if I'm d-dimensional on ground set n, then just take all the d plus 1 subsets I don't see, just like the complement of the graph, right? Okay, and so then this guy will support a minimal resolution of that ideal. Okay, and so again, if you had this is an example of this complex is the x delta bar for an interval graph, where delta is interval, right? And I mean, this is just a consequence that the whole point of cellular resolutions, or one point, is that you can read off the Betti numbers in terms of the F vector, right? They are the F vector, at least the coarse Betti numbers. And so that's what I've written here. Yeah, what's even more sort of amazing or fun is that these maps are also encoded in this picture, right? That how the boundaries relate is also encoding those differentials. And let's see. So one thing you might notice here is you have no, so this is generating degree 2. And these maps are all linear because this is a -3, and et cetera, right? And that's not a coincidence. So, maybe I'm jumping ahead. OK, so I'm going to the second point, is that if you look at this construction, you can actually read off the monomial corresponding to every face. It's just this data tells you the degree of the monomial that's playing that role in that chain complex. And it so happens that you'll always have linear maps, these degree 1 entries in the matrices. So this will always be a linear resolution. I wanted to say that this is generalizing a construction of Nagel and Reiner that they considered for shifted complexes. And, okay, you guys with me? So, yeah?
Complex of boxes? You wrote box of
Yeah, okay, well,
it's complex of boxes.
That's not a commutative thing, is it? Yeah, thanks. Complex of boxes. +1, -1. That's right. And Reiner Nagel, that's okay, right? The Nagel run. Okay, so that's right. Complexes of boxes. Thanks. And we know that interval graphs are chordal, so I think of this as sort of a special case of Froberg's, but also generalization, right? Specialization because I'm only taking interval graphs, which are not all chordal graphs, but I'm also getting higher dimensional things, right? So and here's a question for.
Reiner Nagel only works because Reiner's in the center.
Okay. He commutes with. Okay, I see. let's see. So yeah, here's a question for maybe some people who think about chordal simplicial complexes, at least a couple of people in the audience. How do these complexes relate to these various notions of chordal complexes that we've seen in literature? Maybe I'll just leave it there. There's more to say there. Here's a picture of from our old paper. It actually keeps going, but I chopped it off just so you can sort of see. This is all possible. Well, there's actually 26 examples, but these are all of the complements of interval two-dimensional complexes with their these are the resolutions of them. So the complex would be 1, 3, 4, 1, 3, 5, et cetera, and these are the resolutions. Okay, just flashing that at you. This is maybe not so interesting for this audience, but I mean, the reason I'm sort of talking about this is that in our paper from many years ago, we actually defined what was called a co-interval complex. It was a recursive definition. We defined d-dimensional co-interval in terms of d minus 1 dimensional. And we kind of did this because we could kind of work with these complexes that way. And of course, for d equals 1, they're going to be the complements of interval graphs. That's why we coined that term. Maybe not the best term in retrospect, but anyway, so now the graph will be given by intervals that don't overlap, right? That are disjoint. Those will be the edges. And recently with Bennet and Marta, we proved that these are actually the same. So if you take one of those interval complexes that we talked about earlier, the complement will be this thing that I haven't told you. But, well, now you know what it is because it's, So anyway, so this is kind of how I got back into this world a little bit. And maybe some people are thinking about these things again. Or maybe I sort of skip.
Anton?
Yeah.
So is that the co-interval hypergraphs that you and...
Yeah, we call them co-interval hypergraphs. I'm now trying to switch to, I lost the battle, so I'm switching to simplicial complexes.
But that's not the co-interval simplicial complexes that me and Jonathan and Steve defined.
Okay, I'm going to mention though, at least, well, okay, well, you should talk. I should have looked more closely. I mean, I'm going to mention you in a second.
Neither of our classes contain the other.
Okay, well, that's okay. So that's another question that I'll mention in a second. Maybe I'll skip this for now because I want to mention, I'm going to mention your guys' there's some sort of other work I want to talk about. Maybe one other thing that I think is kind of fun is that, so by definition, this complex that I cooked up sits in this really big product of simplices. It's a sort of big space. That's a big space. And we can do better than that. So we can actually embed this thing in a more efficient way. And so here's some more notation. Delta dn will be the d skeleton of the simplex on n vertices. So that, in particular, that's going to be co-interval because it's the complement of nothing. I mean, it's all possible, right? So it's the all possible edges or facets, whatever you want. And it turns out that you can check that this guy has a minimal resolution supported on a fine mixed subdivision of a dilated simplex. So this is what Federico was talking about. This dilated simplex is really a Minkowski sum of a bunch of simplices. And I don't know if you talked about mixed subdivision so much, but there's a way to think about subdivisions of these guys that are related to triangulations of related objects. And we showed that this complex, and I should have said this, that this resolution is the one that I constructed earlier. So for the complete graph, you're seeing the edges of the complete graph, this is actually supported on this subdivision of a twice dilated simplex where you've got some Toblerones there and some simplici, some tetrahedra there. Maybe familiar picture to some people. And so as a corollary, then for any co-interval complex or complement of an interval complex, you get a cellular resolution supported on this smaller thing. And again, I'm trying to, my sort of pitch to you is that these are ways of picturing these complexes. So you sort of see them now in lower dimensions. And again, we're a little bit in the weeds maybe, but so which particular mixed subdivision do I consider? It's called the staircase triangulation, if that makes sense. I know some people, this is mentioned in the Jesus et al. Book. And what's kind of weird is that not all regular mixed subdivisions work actually in this context. So here's an example I won't really explain. This is a particular downset. This is a mixed subdivision of a 3 times dilated triangle. Turns out that won't work. This is but side note, I just want to maybe advertise some other work that if you take any regular mixed subdivision, it doesn't even have to be fine, and it doesn't even have to be a sum of top dimensional simplices. You can take sums of simplices of different dimensions, these are certain kinds of generalized permutohedra that Federico talked about, you can actually get cellular resolutions of different kinds of ideals there. But if you like mixed subdivisions and resolutions, then there's more to say there. And then, okay, so then some related work. Yeah, so that was fast. Was that make sense? I heard some. Okay, so I want to think of this, this space of edges or a space of facets that I wrote down here. One way to think about this is it's really a moduli space of homomorphisms from a fixed object. I mean, every facet is really just the codomain of a map from the thing that's picking it out. So if you think about a directed edge in a graph, that's just a homomorphism from an edge into the graph. And so you can kind of think more generally that you have just spaces of homomorphisms from some fixed object into your class of objects. And I want to argue that there's other ideals out there kind of defined in similar ways. So Ben has worked on these, that the more general setting of simplicial maps, and maybe you can say more at some point if we want to talk about that. It's, I would say, kind of similar story there, but more general than what I've talked about here. There's also these ideals of poset homomorphisms, which again, maybe not quite the same, but I would say similar spirit. So Martinez worked on that. I don't know if anyone else is here, but and then maybe even stretching this a little further, there's this notion of a path ideal of a graph, right? And that's a generalization of an edge ideal. The edge ideal is just generated by these degree 2 things, and think of that as a map from a edge, but you have these path ideals where you're taking degree 3 things which correspond to paths of length 2, I guess, so 2-step paths. And that I think of as also a kind of homomorphism space. And just again, side note, sort of advertising some other work that I've done recently, so in the past couple years, with Anurag Singh, not the one that probably people mostly know. So this Anurag is based in India at IIT Bhilai, I guess. So we worked on sort of just the question of understanding these spaces in just sort of more topological perspective, say. And we prove, for instance, that if you take the acyclic tournament, right, which is unique up to isomorphism, then no matter which thing you put in this domain, you look at this space of homomorphisms, you get something contractible. And again, this is kind of the thing you want if you're trying to build a resolution. And so you can sort of reverse engineer a resolution maybe, but it'd be nice if there was some kind of natural object showing up there. And okay. So yeah, last slide. So a bunch of questions. I told you how to define this x delta from a simplicial complex, and we saw that it works for these complements of interval. What is the biggest class that it works for? And can you characterize that class? We talk about this in the old paper. You can actually, there's this notion of an interval decomposition of a graph, like sort of breaking it up into interval graphs. And you can use that to actually build resolutions that are not going to be minimal anymore, but for general graphs, you can build resolutions that, it's sort of like it's a generalization of the Taylor resolution, if you know that one, right? Where that just says that a simplex always, a huge simplex, on the generators of your ideal always provides a resolution. That's a particular case of an interval decomposition where the vertices are the interval graphs. But if you have an interval decomposition, then this is a more efficient way to kind of build a Taylor-like resolution. Here's a question we're working on now. Is the Alexander dual of these complexes shellable? Right? That would tell you that the ideals have linear quotients, which is kind of a natural thing people think about. Even stronger vertex decomposable. And then this kind of really general question, homomorphism complexes as building resolutions. I kind of trying to convince you that's interesting. And then I already mentioned this, these interval complexes, there's a whole zoo, I don't know, at least 2 or 3 notions of chordal simplicial complex that I would maybe like to know how they relate to these interval complexes. Maybe people know. Since I put this in to maybe justify my presence here. I don't know much about recognizing graphs, but Wikipedia tells me that recognizing these guys in polynomial time. Is it true for interval complexes? I guess it is true for complexes that have linear resolutions because you can just do that or something to check. but this is going to be a special case of that class, and the question is that easy. So this would kind of give you I don't know, some class of easily recognizable complexes that have linear resolutions. Sounds, computation. Okay, I think that's it. Okay, so thanks.